I would like to talk about magma-carbonate interaction, which I think is a topic that is of relevance, certainly in certain parts of Java, because of the thick sedimentary succession. My talk will be a little petrological, but I know the audience is not just petrologists, so I will try to be general about those things, but I will also talk a little bit about details about geochemistry and isotopes and things like that. So from that point of view, please forgive me if some of the things are a little specific, but overall, I think I hope to be able to illustrate the main point. I have been working in Indonesia since 2001, so it's 22 years now that I work in Indonesia. I have studied at Merapi Volcano, but I also worked in other settings like Krakatau and in Bali, Agung, and I have worked a little bit on Kelut, and I've visited many volcanoes, also in West Java. I've been at Slamet, and of course I've been in Bandung and volcanoes surrounding the area there. And I would be very keen to do more work there in the future. So let's focus on Merapi today, because this is where I did most of the work. And this is something where I think we can learn a lot because it's a very active volcano. So let's come with a general introduction. So magma is, of course, very important because it's a messenger from the interior of the Earth. So a magma that erupts at a volcano gives us a lot of ideas about the source region and also the processes that magma experienced during the journey to the surface. And it also tells us something about the rocks it passed. When it interacts with rocks, when the magma and the country rock, the rock next to it, are interacting, we can usually see that in geochemistry. So lavas erupted at volcanoes is, however, often very diverse in geochemistry. So we need a specialist to understand how to read the information. And petrologists start usually with this concept, the Bowen reaction series, where low silica magmas, basalts that are very hot, they crystallize certain olivines, like certain minerals like olivine and CPX, OPX, plagioclase. And then later on, when it cools, different minerals form, like hornblende, later biotite, and the early minerals stop. Eventually, when we have high silica and the system has cooled, we get minerals like potassium, feldspar, and quartz. And when the crystals form, they change the composition of the liquid because the chemical components are locked in the crystals. The liquid from which they form will change. And this process is often called differentiation, magmatic differentiation. So, and if we look at the theory of this, going back to Mr. Bowen, who did this in experiments already in the 1920s, then we should start with a lot of basalt, and we distill rhyolite from this, from a low silica to a high silica rock. But if we look at Indonesia, in general, the volcanic rocks are very differently distributed. There we have not so much basalt at the surface, but a lot of andesite. A lot of typical rock in subduction zone type volcanoes is andesite. And we have a bit more rhyolite than we would expect. So something doesn't quite work according to the Bowen reaction scheme. And if we go to continental settings like New Zealand, which is a continental fragment from Australia, then the Bowen reaction scheme is exactly the other way around. It's upside down. So the conclusion from this is that we must think about in processes in addition to just mere or pure fractionation, pure differentiation from the Bowen reaction scheme. And this is what I want to talk about today. Is there other processes going on? And this is the big question mark here in this slide. What happens when we make magma in the subduction zone, factory as some people call it, and the magma rises up into the crust, and then we get explosions. What we make is basalt, but what we erupt is often andesite or even rhyolite. And therefore, the question is, what happens on the way? And this is what I'd like to talk about in more detail today, using the example of Merapi and also work out whether these processes have an effect on how eruptions progress. So the whole goal is to provide a tool to understand the hazards at these volcanoes a little better. So I'm going to talk a little bit about Merapi volcano, and then we're going to look at some petrology and mineralogy, and then I'm going to look with you at the calc-silicate inclusions at Merapi. They have become a little famous now because it's a very interesting type of rock that Merapi produces. And then we're going to do a little bit of geochemistry. We're going to look at isotopes. And I hope those who are not so interested in petrology can appreciate some of it. I'll try to make it general. And then, of course, I'm going to provide a summary of what I think is going on under Merapi and maybe some other volcanoes in Java as well. So let's start. Indonesia, as you all know, has many active volcanoes, and Merapi sits here in central Java. And then, of course, there's many volcanoes in West and East Java. And I hope that some of these ideas can be tested at some of the other volcanoes. But for today, I'd like to start with Merapi. It's one of the most active volcanoes, and it has explosions. And it was chosen a decade volcano in the International Decade of Disasters from 1990 to 2000. So it was recognized as one of the very dangerous volcanoes. It has periods of dome growth. They are on the order of tens of years, but then it also has very short explosions. And they often are very difficult to explain. They don't necessarily have seismicity coming from depth, but they actually have only activity in the crust. And this is a puzzle. It's very difficult to predict or forecast these eruptions. The area around the volcano is very densely populated. The population density on the flank of the volcano is over 500 people per square kilometer, so it's pretty high. And then it caused a lot of casualties, well over 1,000 casualties in the last 100 years. The big eruption in 2010 had over 300 people that perished. So there was the area in the forbidden zone, the area where you shouldn't be if there's an eruption crisis. But in 1994, there was also people being killed outside the forbidden zone. So it means we still don't understand the volcano perfectly. So, and this is the problem here. Prediction, as I said, of the explosive events remains a challenge. It is difficult. We don't quite sometimes understand what are the processes leading to eruption and to explosion. So here I'm trying to talk a little bit more about this, and I got strongly involved in 2006 when the 2006 eruption commenced. It started in March, and in March we had higher earthquake activity, higher seismicity. And I've been very busy the last few days. You may have heard there is higher seismicity in Iceland for the last week. We are worried that there is an eruption. So I have also the webcam on to see whether Iceland erupts. Maybe that is a part of the technical problems I have right now. So, so it starts with increasing seismicity. And then we had the first pyroclastic flows in 2006 on May 11th. And then this continued to erupt. And in mid-June, we had the highest activity. There was an earthquake at very early in the morning on Sunday, 27th of May. And following that earthquake, we had a lot of pyroclastic avalanches, and they increased the dome growth. And we had a reaction between the earthquake and the eruption. So here in the diagram on the bottom right, you see the days of the eruption before the main earthquake on 27th of May. And then we had the big earthquake, and then the activity of the volcano increased dramatically. And these earthquakes, they're not deep subduction earthquakes, they're crustal earthquakes. So they're shallow, they're in the crust. And here's a few impressions. The consequences were severe. The earthquake was very strong, and 6,000 people perished, and more than 1 million people were homeless after this. The main earthquake epicenters were in the area a little bit to the right of the Opak River fault in the Graben area in the valleys to the south of the volcano. And it is an area that is densely populated because this is where Yogyakarta city is also located, and it's very fertile. Excuse me. It's very fertile land, so a lot of agriculture happens there, a lot of people live there. So here's a few impressions, and the earthquake devastation was, of course, severe. So I don't want to go into detail. It's not a nice kind of set of images, but here even the university in Yogyakarta, that's Gadjah Mada University, was severely damaged. And then, of course, the population was affected. Many people were homeless for a long time. It's a very severe situation, and I think we need to understand the volcano a little better. Many people lived in shelter. Schooling was in shelters for a long time for many people. And then on June 14th, it got even worse. We had a pyroclastic flow, and the village of Kali Atem got destroyed. The village was evacuated, so this was good. So the people in the village did not die, but there was 2 volcanologists, and they worked in the observation bunker. And this is the image in the bottom here. This is the bunker. And there, 2 of the volcanologists from the observatory were stationed, and they were buried in there, and they did not survive. So the big question I had at the time is, what makes Merapi so dangerous, and why is it so explosive, and why don't we understand how the eruptions work? And in the bottom right here on the slide, I'm showing, can I see this? Can you see the cursor? I don't know, maybe not. But in the bottom right here, there I show an inclusion. This was actually revealing because the lava was not pure. It had many, many inclusions. And this green type inclusion, you don't see it to start unless you focus on it. But then I realized there's something going on. So, and once I started to look, I found many, many inclusions. And it starts off with this type of inclusion, which I called andesite in andesite. So I realized it's not just one type of magma, it's actually several types of magma. They're chemically very similar, but not identical. And there is these inclusions, these green and white ones. They are calc-silicates. In Sweden, we have an old mining term that was coined by the miners. When they saw rocks like this, they called them skarn. Skarn in English would be translated to something like rubbish. It's what the miners didn't want, and it's a reaction product between magma and usually sedimentary rocks. So here's another one of these skarn or calc-silicate inclusions, and you can see it's embedded in lava, and it is zoned. It starts from green, going to cream, going to white color. So this tells us there was a chemical reaction from the outside to the inside. And this is very important. The outside is very diopside rich, and the white mineral in the inside is wollastonite. And wollastonite is a reaction product between carbonate and magma. And this was very important to realize. So, but there's many other inclusions. Once you start studying inclusions at volcanoes, you find a lot of them. We also found some basalt inclusions. We found plutonic inclusions. The specific name for this is diorite. And then we have megacrysts of amphibole here, for example, very large, up to 10 centimeters large. And then we have partly digested rocks. Here you see the little holes. The magma was eating the inclusions. So again, reactions going on. And of course, the calc-silicates. And some of them were really large, football size. And there you can see reactions as well. And you can see a lot of vesicles surrounding the calc-silicates. So what I noted was that there is something going on. And of course, there's many, many crystals that makes the magma very stiff, and the crystals are zoned. And this, of course, might also give us information. So I will focus on these inclusions now for a little while to understand the system below Merapi a little better. So we must think about a magma reservoir, a magma chamber under Merapi. And in the observatory, there's this wonderful old model that is many, many decades old, and it shows that there is a big magma reservoir under the volcano and a little magma reservoir inside the volcano, inside the cone. Well, this is a bit more difficult in reality, I think, and in magma chambers we have a lot of processes. Petrologists like to understand what happens in magma chambers. So there we have new magma coming in, causing mixing. We have crystals that settle, we have convection, we have interaction with the country rock, we have gas escaping. So there is a lot going on, and these inclusions can help us understand this. And I should point out that this little magma chamber that is inside the volcano in the high level, that was postulated from seismic evidence as well. And there was a very interesting paper by Ratamo Purbo. He was the head of the observatory at the time, and they found a little seismic gap, a circular gap at about 2 to 3 kilometers under the volcano. And the interpretation was that this is this little magma chamber that sits inside the volcano. But another study later on in 2003 could not find it again. So it was a big discussion at the time. Does the magma chamber exist? Does it not? If it exists, can it cool down? Can it freeze? Can it get reactivated? Many, many questions about what's going on inside the volcano. So we tried to answer some of this from a petrological side. If you have plutonic rocks, you must have a magma reservoir. So my postulation is there is magma reservoirs, there is magma chambers. And when we look at these rocks here and we can determine the crystallization pressures, the barometry as we call it, then we find that these different type of rocks, they have crystallized at different levels. The amphipole crystals have crystallized very deep, 25 to 35 kilometers deep, and the pyroxene crystals, the tiny little black ones in the upper photo inside the white rock, they are deep but also shallow. So they tell us there is a deep reservoir, but there's also something going on very shallow inside the volcano. So we must think about more than one magma reservoir. That's what the rocks tell us. So my continued work then was looking at the various inclusions, and I'll give you a summary here. I don't think we have time to go into very much detail, but the different rock types, they come from different levels. The very mafic rocks, the gabbros, they come from very deep, 30 to 20-ish kilometer. The basalts come from a little shallower, 20 to 15 kilometer, and the diorites usually go all the way up to the upper crust, up to about a few kilometers depth. So that implies there's probably many little magma chambers, not just one or two, but many small pockets as we postulated it at the time. So if this is true, then we might have little reservoirs that exist for some time, and then they cool and freeze, and then they exist again if new magma comes in. And this makes it very complicated for anyone to understand the volcano if this is real. There was a seismic tomography study done by in the Merapi project, which was partly coordinated at GFZ in Potsdam in Germany, together with the Merapi Observatory. And they found that there's a big anomaly under the volcano and also under the old volcano Merbabu, which sits just to the north. And this red area here is an anomaly that implies this could be high fluid content, high magma content. And if we take our barometry data, we cannot say anything laterally in barometry, but we can go into depth. And then our depth data, they fit the anomaly rather well. So we were very positively surprised how well the seismic data and the barometry actually fit together. So we need to think about a fluid, a complicated fluid or magma system that feeds the volcano. And it's not a single system, it's not a stagnant system, it's a dynamic system. So we did similar work in other volcanoes, and there we looked at various distribution models. We're still working on this. We had a paper a few years ago in 2021 where we looked at the supply systems for the Balinese volcanoes, but also Kelut, Merapi, and Krakatau, the example of Anak Krakatau. And there we find that many of these volcanoes seem to have many different little reservoirs, some of them very shallow, and we call them sharks, shallow arc magma storage. These shark reservoirs, they may not be always there. They can exist and then they can stop or freeze over, they can cool, and then they may come back. And for Merapi, I'm showing a little diagram on the right-hand side where we look at these little pockets or reservoirs, and what we realize is that some of these pockets, they must sit in the upper crust. And the upper crust beneath Merapi is actually made dominantly of sediments, and it has a lot of limestone. And this, of course, is the problem with the magma-carbonate interaction. So we then tried to test the crystal record a little more. So we looked at the crystals, and we believe we can read crystal zoning like we can read tree rings in botany. So we started a bit naive, maybe thinking it will be very simple. And once we looked at the crystal record, we realized it's very complicated. We have a lot of chemical variation, and this is expressed here as anorthite, AN on the diagram. This is an expression of calcium. So it's the calcium component in the feldspar. And the higher the calcium, the more primitive, the more mafic the magma is. The lower the calcium, the more felsic, the higher the silica content is. So here we have variations from very low calcium cores to high calcium rims and going backwards and forwards. And we realized very quickly, this is not simple. This is not at all what we would predict from Bowen. So we have some crystals with high calcium cores and other crystals with low calcium cores. And the rims can be different as well. And it was very confusing to start with. So when we look at this diagram here, we would think that basalt produces high calcium, high AN content, and andesite would produce AN50 type rocks. And the variations would imply that we are going backwards and forwards. So this is complicated, as I said, and the model at the time was, if you have situations like this, then you can think about a reservoir high up and a deep reservoir. The deep reservoir has high calcium crystals. The shallow reservoir has lower calcium crystals. And if you bring magma from the deeper one to the higher one, you can mix the magmas and you get different types of crystals. So the idea would be that recharge could actually cause this complicated type. That was a very good model at the time, and this was about 15 years ago, and it was widely accepted, and we started to think, okay, let's work with this model. So then we looked at the crystals in more detail, testing this model further, and we used a very interesting device, and we have one here in the laboratory in Uppsala, and I think it's great for doing detailed work. So if anyone is interested, this is something we can use. And you can drill little parts of crystals. It's like a dental drill. When you go to the dentist and they drill, they have a drill, and we have it on a microscope. So we can drill little zones or little areas. And let me tell you a little bit more about this. So here we have the drill bits. They are diamond bladed, and they can remove tiny areas, micron-sized areas from crystals. So there's a computer that controls it, and we can say what we want to drill, the core, the rim, or certain domains. And we drill it under clean water in a water bubble, distilled water. And then the flakes of the crystals are in the water bubble. And then we take the water bubble, we pipette it off, and we can use it for the work in the laboratory. So we did this, and I had a PhD student, Jane Chadwick, doing this, and we analyzed this for strontium isotopes, because strontium isotopes would tell us whether the magma comes from deep, because then we have low strontium isotope ratios. If the magma comes from shallow, then likely it has higher strontium isotope ratios because of crustal interaction. But to our surprise, we found that the high AN, the high calcium areas, actually had variable strontium isotopes. And the high AN values, like in the right-hand example, turned out to be having very elevated strontium isotopes in some cases, but not in others. So we got again very confused, and it was very complicated. So here's two examples. Sometimes we have high strontium isotopes, that's the colorful bars, that's the analysis, with the errors. So this is why the bars are a little wider. So you see that sometimes the values are jumping up and down and up and down. So again, it was not systematic, and it gave us a lot of puzzles to think about. So here, for example, we have this crystal. This is a microprobe traverse with a high calcium core. And we have, for example, the magnesium, and there's an anti-correlation. So we see that the magnesium content is actually going down, while if we expect it to be basaltic, the crystal, it should be going up. So we had some real problems here, and we looked at the strontium distribution of all the data in the literature, and the Merapi basals, the old data, and the recent Merapi whole rocks, WR, they seem to increase towards the right. And if we look at the feldspars, they go even further right. And to the right, well, there is crustal rocks only. So magmatic is to the left and crustal is to the right. So we realized we were looking in the wrong direction. We have to look at the crust in more detail. So this brought us back to the sediments. And then we looked at these calc-silicates, or skarns, as we call them in Sweden. And we realized that whenever they're present, there's often a lot of vesicles, a lot of bubbles, as you can see in the image in the lower left. So, and the inclusions were actually interacting with the magma, and there's a microscope image in the top right, and you can see that some of the crystals from the inclusions are actually incorporated into the magma. And that made us realize, oh, some of the feldspar crystal cores are not magmatic. They actually come from the sediments, from the calc-silicate inclusions, because they should have high strontium isotopes, but because they come from limestone, they should also have high calcium. So they're not at all from the volcano originally. Many of the crystals may actually come from the crust. And this helped us to understand things a little better. And then, of course, we went into the area surrounding the volcano, and there is a lot of limestone. Here's a limestone quarry in the outskirts of Yogyakarta city. And there is so much limestone that suddenly we started to see a picture. The magma and the limestone together explains the different complex situation we see in the inclusions, but also in the crystals. So when we look at the limestone and the inclusions and we analyze them for strontium, we find that they are further to the right in strontium, and that's the answer. Why some of the crystals are so complicated and why we are seeing a higher strontium isotope signature in the younger rocks of the volcano. The older the volcano, the more the interaction with the crust. And this really opened our eyes to seeing that the volcano is not just isolated, it actually interacts with its surrounding. So when we look at the crystals then, again, and we had almost 2,000 analyses of crystals, we realized that there is two populations, broadly speaking, a high AN and a medium AN, a high calcium and medium calcium distribution. And we also looked at the feldspars in the calc-silicate inclusions, and we see overlap, as you see in the bottom left diagram. Many of the calc-silicate feldspars, they are very high AN, and that overlaps with the high AN in the lavas. So we realized, oh, many of these crystals, they come from the crust. And if we look at this for all the inclusions, we did a lot of work there, and then we find that the shallower the rocks have crystallized, the more of this crustal influence we see, and that the local crust is the extreme value with the highest strontium, and that's causing this shift. So the conclusion from this is, from the rock record, we must have interaction between magma and limestone. So we wanted to test this further, and now it gets a little detailed on the geochemistry, but I'll keep it a little superficial. So I started off with a paper in 2013 in the top left doing oxygen isotopes, and what we found is that, again, the lavas and crystals, they do show a variation from mantle, which is the vertical dashed field there, and they move towards the local crust and calc-silicates. And my student, Frances Degen, and now a researcher here at Uppsala University, she did this in much more detail, and that's the lower diagram. And she wrote a summary paper just this year, was published in January. And I'm going to say this later. If anyone wants a copy of the paper, I can very happily send it by email. Then we see that there is a strong shift. And it's a good set of data. It's a lot of analysis. And we have also intracrystal analysis now due to Frances Degen's work. And there we see that there is a shift, and the influence of the crust is very clear. We then try to quantify this in various attempts. And I show an early attempt to the right. This is from my paper in 2013. And there we see that the green and red data, that's the pyroxene and feldspar data. And then the blue data is various inclusions and crustal rocks. And we see that the Merapi data, they shift from a magmatic trend, which would be the Rayleigh fractionation trend. They go upwards, meaning they are displaced towards crustal rocks. This allows us, this is not so good. This allows us, here it's coming. This allows us to make some prediction about how these interactions work, and therefore we looked more carefully at the crustal inclusions again. So here I'm showing a few more of these examples, and the interaction between the magma and the crustal inclusions, they are very intense, and there we have these vesicles. So we realized not only does the chemistry of the magma change, but likely also the way the volcano erupts. And I'll talk a little bit more about this. So we studied these inclusions in detail, and again, I don't want to talk too much about it, but if we look at the mineralogical changes, we see that typical reaction minerals like wollastonite, they form in the interaction zone, and the diagram on the bottom right is from the host rock, from the lava into the calc-silicate, and we see that the minerals change systematically. So this gives us a very strong indication that the chemical reactions are taking place. More recently, there was a PhD student in the UK, Jean Whitley, and he was working together with Ralph Gerteser and Frances Degen and Ralph Alama and myself. And he looked at some of them in much more detail when it comes to the minerals. And if you like, he published a paper in Journal of Petrology, and there you can see all the detailed mineral variations that come from the reaction. The important realization is that these reactions, they change the minerals, but they also produce a lot of CO2 that is liberated from these reactions. And this was very important at the time. So here's more reactions, and in some of the places we see that calcium was moving into the magma, magnesium was moving into the inclusions, and there is partly some calcite left in the inclusions, but most of the calcite was replaced with other minerals. So the big conclusion, as I said, is that a lot of gas, a lot of CO2 from the limestone had to be produced. And you all know when you put acid on limestone, the limestone starts to fizz. It produces a lot of CO2, and that CO2 is coming through the volcano. So We looked at where this happens and at what temperatures it happens. And in the study by Whitley, there is some thermometry, and there we find that it was all happening at very high temperatures. So it is the volcano doing this. It's not anything else. So in the upper crust, there is a lot of carbonate, possibly up to 10 kilometers, and the magma is reacting with this, causing mineral changes in the reaction aureole, but also producing a lot of CO2, and the CO2 has to go somewhere. So we did some experiments now. This is work by Francis Degen again, and this is experiments where we tested what happens if carbonate and magma comes together. The experiments were done at INGV in Rome, in Italy. That's the National Institute for Geophysics and Volcanology, and they have this beautiful apparatus, a piston cylinder, that allows to simulate magmatic conditions under pressure as well. So you can test how things are inside the volcano. So what we did is we took a Merapi magma rock and we melted it, and we had carbonate flakes in there as well, and you can test the interaction. And we were so surprised. The interaction is very, very fast and produces a lot of CO2. So let me show you a few examples. So here we have a 0-second experiment on the left, in the bottom left. And 0 seconds means the experiment was heated up. It takes about 6 minutes to heat up. And then we stopped the experiment. And then we had another experiment with the same setup where we let it run for 60 seconds, 1 minute. And all of the carbonate was gone, and we see all these bubbles on the right-hand side. So a lot of gas is produced. And we did this for various combinations, and we found if a lot of water is in the magma, the reaction is even faster. If the magma is dry, it's not so fast, but overall, it's literally so fast. You can, look at your watch, and this is very shocking. We realized that this could be a real problem for the volcano. So we did a lot more work, and led by Francis, and there we look at the details inside the experiments. And again, it's published. You can look at this in more detail, but we saw that the magma is, of course, contaminated. It's receiving elements from the dissolution of the carbonates, but it also makes these large bubbles, the round, large black areas. This is bubbles that we see under the scanning electron microscope. And we have very recent work that Francis shared with me the other day, and she now informs me that we have some good indication from the composition of some of the gas in the bubbles, and it's dominantly CO2. What we did in published work was we looked at the strontium, of course, with strontium isotopes. We drilled them as well, like with a little dental drill on the microscope I showed. We drilled the experiments on very small scale. And the red areas in the upper diagram, they are drilled areas. And we find that, of course, they show the strontium is affected by this. So on the right-hand side, I'm showing the experimental contaminated glasses, and they fit exactly the natural trend from the basaltic rocks at Merapi to the feldspars to the crustal rocks. So we were able to reproduce in the laboratory the trend that we see at Merapi in nature. So these piston cylinder experiments are not only telling us a lot about the chemistry, but just from a textural point of view, they're beautiful, because there's this one experiment in the top left here, where we see this finger of lava going into it and a lot of bubbles. And then we look at the right-hand side, there's a finger of lava going into one of the calc-silicates, and we see a lot of bubbles at the reaction. So I was just impressed how well these experiments reproduce nature. And we really think this is a big answer to our question, why Merapi is so temperamental, why we have these short-lived explosions, because these processes are very fast. So in simple terms, if we take a carbonate from the crust and we add magma, we produce minerals like wollastonite, the white mineral in the inclusions, and we produce a lot of CO2. and large quantities of CO2 may be liberated. And this is consistent not just with the chemistry, but also with the textures we see. So, and if this is true, then we produce a lot of overpressure in the volcano, and this can make very unpleasant explosions. So we wanted to test this further. The rest of the talk is more about how the volcano reacts to this and the consequences for the eruptive behavior. So we looked at stable isotopes. We wanted to see what the stable isotopes do to understand this better. And here's a plot of carbon isotopes now versus strontium isotopes. The carbon isotopes are from gases. And what we find is that Merapi gas is not just from the mantle. It's not pure magma. Merapi gas is displaced towards sedimentary rocks. In this diagram, we cannot say which sedimentary rocks because the upper crust and the subducted sediments, they're very similar, but we can say that sediments play a role. So here we see there's more of this phenomena. We also see that when we have degassing going on the top, we see a theoretical model about degassing. When we degas, we're going from right to left, then the values are going down in the degassed rocks, but the values in the gas are on the right. So in the bottom diagram, we see that the calc-silicates and the lavas are very much to the left. They have lost their gas, but the gas is coming out at the volcano is very high. It's fumarole gas here in the diagram, and that is elevated from the mantle values, which is the blue vertical bar. So we had more work done by Jean Whitley, and I will not go into details, but he did a lot of ion probe work, and that was carbon isotopes and oxygen isotopes, and you can read the details in the paper from 2019. But the different samples are given in different colors, and what we find is that very frequently we have reactions between the limestones, the marine limestones, and the magma, which is igneous. So we see all various reactions there, and it implies a lot of gas was lost from the calc-silicates. So if we look at the modeling there, then we can see that many of the reactions were not complete, and we have made some calculations. And if we look at the various calculations, then we can estimate how much CO2 would be produced. And we did various calculations for what scenarios, like the 2010 eruption, and we come up with various numbers here. And I don't want to go into detail, but I want to put it a little bit in perspective. If we take all the limestone under Merapi in a cylinder, and we take it as 1 kilometer wide, which is not so much, but we take it as 10 kilometer, the entire sedimentary thickness, we produce 3.8 to 10 to the power of 13 kilograms of CO2. That's a lot of CO2. So let me put that in context. This is, of course, we all have to think about climate change. This is about the amount we produce in a single year from all industry on Earth and all fossil fuels. So we produce 38 gigatons, and all fossil fuels from industry at the moment, as you see in the diagram, produces 34 gigatons. So plus minus at these scales, 1 gigaton is not the issue, but actually the calculation says Merapi would, over its entire life, produce more CO2 than what all of the industry on Earth produces in a single year in terms of CO2 output. It's a lot. So, and of course, Indonesia has many volcanoes. So this is a big issue. So let's check the gas now. We're coming towards the final parts. And we wanted to now see if all of this is true. So, and you can only test it by going and sampling the gas. So we went up the volcano, and it's a tall volcano. It's a long hike, but it's very enjoyable. And up there, the air is a little thin, but you get fumaroles, of course. So on the left, I'm showing the dome and the dome complex. And then on the right is when we sample gas. And this is how it looks up there. It's very cold early in the morning, and it's intense because you need a gas mask, of course. And here's our data. We have, first of all, a literature timeline, and the green dots, they are our data. And the first observation is the entire Merapi baseline is elevated. It's higher in carbon isotopes than other volcanoes. For comparison, I'm showing Krakatau data we also collected, and Krakatau is very low, -7 on the delta 13C, while Merapi is much higher. So this already tells us that Merapi has a lot more sediment or carbonate interaction than Krakatau, and I'm showing what marine carbonates should have in the top. That's the blue area. So we are pushing the values up. The gas clearly has a contribution from limestone. And in addition to that, we sampled in 2006 after the big eruption. Right at the end of the eruption, we climbed up there. It was still erupting, but it was safe enough to sample gas. And what we noted is that during the eruption, the values were even higher. This is the peak there in 2006, and we sampled a little after the earthquake. And we realized that there is a link, that the baseline is already high, but when the eruption happened and the volcano is shaking up the country rock, we get even higher values of CO2 coming from the crust. And we realized the interaction between the lava and the carbonate is a serious problem at Merapi. So just a very quick note, helium isotopes, another method you can do on the gas, and don't want to give you too much of details here, but you can look at the helium isotopes. 3 and 4 is the ratio. The atmosphere values are very low, and that's making this a good tool. And if you look at the Merapi gas, you will find that it is actually offset. So the crust is very low on this scale, and the mantle is a little higher. So here I'm showing crust and arc type volcanoes. And if you do this, then what we find is that the gas at Merapi has approximately 25% CO2 coming from the limestone. So there's a large contribution from limestone, if these data are correct, that is, of course. So we can then make a little model calculation. If we have an eruption and we have a magma chamber, and we say the magma chamber is 800 meters tall, which is about the seismic gap of Ratamapurbo, as I said earlier, and we make it a little more than 1 kilometer wide, and we sit in limestone completely, and we drop a block of limestone into this magma chamber, and for the calculation, we assume a block of 80 meters, so 10% of the magma chamber height. We would produce 60,000 tons of CO2 in a single week. And this is a lot. At the moment, we have 700 tons on a quiet day at Merapi. So if a block of limestone falls into the magma, we would get a vast amount of CO2, and likely very quickly, as our experiments have shown. So if you want to produce the same amount of CO2 from new magma coming from depth, you need a lot of magma. It would fit into a cube of 440 meters side length, and that would be something with sea and seismicity. So since some of the eruptions don't have deep seismicity, I think some of the eruptions at Merapi can be explained by interaction of lava with limestone. And that is good in one way because we start to understand what's going on. It's bad in another way because we cannot actually make any sensible forecasts. We cannot tell when this happens. So limestone assimilation may be very effective, and it may be an explanation for some of the unexpected, unforecasted explosions at Merapi. So it's a serious alternative to explain the phenomena, but it's not necessarily a big comfort, because it means Merapi is temperamental and will stay temperamental. So let me bring this together. I'm summarizing now. We have a subduction zone in Indonesia, in Java, of course, and we produce deep basaltic rocks. This is from the Degen et al. Summary paper that we just published. And this magma is rising up. It's taking different reservoirs through the crust, initially in the crystalline lower crust, but eventually it reaches the upper crust, and there we have magma-carbonate interaction. And that is a problem. And Merapi sits right in the Kendeng Basin, which is very thick sediments, and there Merapi is a particular problem. So this is a feature that has been increasingly recognized now. When you look at the publications, only in the last 20 years have the publications on carbonate interaction magnified. Suddenly there's a lot of magma-carbonate interaction papers, and this is Scopus data. So people only now, over the last few decades, realize how important this might be. However, having said this, some early workers worked on this already in the 1920s, like some of the Dutch geologists. They realized that this may be a problem, but it wasn't taken seriously into account, and this is only something we start to understand now. So what happens beneath Merapi? Quick summary: we produce basaltic magma deep in the subduction zone. This rises up, and it then produces little reservoirs in the crust and the lower crust up to the middle crust. And there we have classic magmatic processes, of course. But then we have frequent recharges keeping the system alive, and that means also frequent earthquakes, and this shakes up the system. We get interaction between the reservoir and the surrounding rocks, and eventually that means we have carbonates falling into the magma chamber, cracks forming, magma intruding, and we can have very quick reactions between some of the limestones and the magma. And we argue that this can be an explanation for some of the unexpected explosive eruptions at Merapi volcano. So how do we picture this inside the magma reservoir? Here's a drawing that was done by one of my PhD students. In the lower right, we have the magma. In the top left, we have the carbonate. Then the reaction, the skarn or calc-silicate reaction, is in between. And in case of a big earthquake or some big recharge or so, we might actually crack the country rock. We might crack it up. We create fresh reaction surfaces. And this may be an explanation for why in 2006, the eruption that started and had an earthquake suddenly got even stronger, because maybe carbonate fell in, produced a lot of extra gas, and made the volcano extra explosive. So this is how it looks at the surface, and I predict that much of the gas coming out of Merapi is actually CO2 from the limestones. And with this, I'd like to draw attention to our new book on Merapi, which was published this year in January. And if you like, please email me. I'm very happy to send you individual chapters. I am not allowed to send the full book, but you can ask for chapters. And you can ask, for example, for the chapter on the research history. It's led by Ralph Gerteser and myself and some others. It's very detailed. It was highly praised by the Geological Survey in the US. It summarizes all the early work, Javanese accounts, Dutch accounts, modern accounts. Then there's a chapter by myself and Francis Degen on the structure and the plumbing system. And specifically for this talk, there's one chapter on magma-carbonate interactions, summarizing all the work I've been talking about, which was led by Francis Degen and myself and a few other people that are involved. So I'd like to say thank you for your attention, and sorry again for the initial technical trouble. You can see many of the articles are on my webpage, which I give here, and also some of the things are on my little YouTube channel, which you can find under YouTube Valtro. So thank you, and I hope it gives you a little bit of a background on the recent work on magma-carbonate interaction at Merapi in Indonesia. Thank you.
Thank you, Professor Valentin Tual. We will do a Q&A session.
Absolutely.
Yeah.
Thank you.